Hello students, welcome to Sauras's classes. This video is Infinite Series Part 4. Now let's start this video with positive term series. Term series. Now what is positive term series? If all the terms after first few negative terms in an infinite series are positive, then such a series are called positive term series. That is, if all terms after few negative terms in an infinite series are positive, then such a series is called a positive term series. For example, minus 10, minus 6, minus 1, plus 5, plus 12, plus 20, plus so on. Now, if we omit this first few negative terms, then all the terms of the series would be positive. So, this series is positive term series. And as previously stated, that addition or deletion of a finite number of terms does not change the nature of infinite series, therefore omission of these few negative terms will not change the nature of this positive term series. Next is necessary condition for convergent series. It is that for every convergent series, un limit n tends to infinity, un should be equals to 0. So, for every convergent series denoted by summation un, limit n tends to infinity, un must be equals to 0. Now, let us prove it. Now let Sn is equals to u1 plus u2 plus so on till un. Now limit n tends to infinity, Sn is equals to k. Now since the series is convergent series, then limit of Sn should be a finite quantity. Also, limit n tends to infinity, Sn minus 1 is also equals to k. So, we have our un is equals to Sn minus 1. So, limit n tends to infinity, un is equals to limit n tends to infinity, Sn minus limit n tends to infinity, Sn minus 1, which is equals to k minus k, which is equals to 0. So from here we get that for every convergent series, limit n tends to infinity, un is equals to 0. However, the converse is not true. That is, if converse is not true. That is, limit n tends to infinity un, if it is equals to 0, this does not mean that the series is convergent. For example, for series 1 plus 1 by root 2 plus 1 by root 3 so on plus 1 by root n plus so on, this series here un is equals to 1 by root over n. So limit n tends to infinity un is equals to 0. But this series is a divergent series. As our Sn is equals to 1 plus 1 by root 2 plus so on till plus 1 by root n, which is greater than 1 by root n plus 1 by root n plus 1 by root n, this is n times. So this is greater than n divided by root n, so it is greater than root n. Now limit n tends to infinity root n is equals to infinity, so our limit n tends to infinity Sn would also be equals to infinity. So even though limit n tends to infinity un is equals to 0, the series is divergent. Hence, this limit n tends to infinity un is equals to 0, this is a necessary condition, but not sufficient condition for convergence. Next is Cauchy's fundamental test for divergence. It is if limit n tends to infinity un is not equals to 0, then the series is divergent. Now suppose we have a series 1 plus 2 by 3 plus 3 by 4 plus 4 by 5 plus so on till plus n divided by n plus 1 plus infinity. Now here un is equals to n divided by n plus 1. So limit n tends to infinity un is equals to limit n tends to infinity n divided by n plus 1, which is equals to limit n tends to infinity 1 n plus 1 divided by n plus 1 minus 1 divided by n plus 1, which is equals to limit n tends to infinity 1 minus 1 divided by n plus 1, which is equals to 1. So limit n tends to infinity, un is equals to 1, thus it is not equals to 0. Hence, by Cauchy's fundamental test, this series is a divergent series.